So, of course, you think of OLS first to conduct regression analysis for examining statistical associations between variables, and it makes totally sense. It is the first regression technique you hear of for sure. It's in the repertoire of the Statistical Association 101, and OLS is very informative. However, OLS needs a bunch of assumptions regarding the data at hand to be satisfied. If these assumptions are not met, results from OLS can be biased or misleading. And now guess, OLS assumptions are seldom fully met. Hence, to get stable results, we must apply robust regression techniques. That is, techniques that do not need some of the assumptions to be satisfied. Starting with a scenario in which our outcome variable is ordinal, but OLS needs the outcome variable to be at least interval scaled. To apply a robust regression technique here means just not to use OLS, but an alternative. However, for starters, let's describe the dependent variable formally. As an ordinal variable, the values of y represent ordered categories. The distances between the values are meaningless. So for each of the categories, we can assign rank, saying that category 2 is higher than category 1 and lower than category 3. And that's it. We cannot say how much more or less a category than another is. But the OLS regression coefficient would try to tell us this. By how many units is y larger or smaller if x is 1 unit larger? Now, instead of modeling y on a continuous value range, we're modeling the leap from one category of y to another. A positive or a negative effect of x on y then means that the higher the value of x, the higher or lower the category of y predicted by the model respectively. In detail, this is done by modeling the probability of y takes the higher category among all adjacent categories. As always, x is a vector of independent variables and b the vector of the respective regression coefficients. The model wasn't a model unless it was able to predict the specific category y takes conditional on x. Therefore, cut points must be estimated. You can read the cut points like how large the scalar bx must be to predict y is taking the categorical value k or a higher. It's clear then that the cut point for the first category is negative infinity. The scalar bx is always larger than minus infinity in the same way that y is taking the smallest category or a higher, which is y is taking a category at all. Put it in other words, we're modeling the cumulative probability of the ordinal variable y. And this is what the formal model looks like. Okay, then let's go through this with an example. I have selected the PISA 2022 data provided by the OECD, not the whole data from all participating countries, but the German subset only. As dependent ordinal variable, I use the proficiency level in the math domain. I define 6 levels. For the ease of demonstration, I use just one independent variable, specifically the mathematics self-efficacy of the students. By having a look at the distribution of the dependent variable PLM, the propped link function seems appropriate to model PLM. Okay, we have our model, the probability of PLM taking category K or a larger one, conditional on the independent variable mathf. All right, so let's run the machine to get the estimates. At first, B1, the regression coefficient of mathf, shows a positive effect on PLM. The higher the mathematics self-efficacy of the students, the higher their proficiency level in the math domain. The first cut point, of course, by definition, is minus infinity, since the probability of PLM taking level 1 or a higher must be 1, regardless of mathf. The second cut point is an estimate, and it is minus 0.743. That is, to predict PLM taking category 2 or a higher, the scalar bx must exceed minus 0.743. Because there is only one independent variable in the model, we can calculate the math score that equals this cut point. We're doing so by dividing the respective cut point by b1. For cut point 2, this threshold is a math score of minus 2.89. And here are the estimates for the cut point and the respective Martha thresholds appearing in the plot. Okay, so this was how to deal with an ordinal dependent variable in regression analysis. But OLS assumptions also can be violated with a metric dependent variable, specifically by a heavily skewed or in some way non-symmetric distribution of y. In such a case, ordinal regression, as just discussed, is not an option, because the values of y do not represent categories and the range of possible values can be very large, maybe infinite. But in an ordinal regression model, cut points must be estimated for each value of y. Doing this would raise the number of parameters to be estimated and hence decreases the degrees of freedom dramatically. So, robustness must be introduced in another way, namely by transformation of y and by the adoption of the regression technique. First, let us take a look at the transformation of the dependent variable. In fact, the regression is no longer supposed to use y as a dependent variable, but instead its cumulative density, represented by the mean relative ranks of y, here referred to as y asterisk. This transformation, or alternative to the original dependent variable, reduces skewness by flattening out the distribution, and outliers are brought home. The model formulation is the conventional linear form, a constant value, aka the intercept, a vector of independent variables, and a vector of regression coefficients. As you can easily see, this model is very parsimonious compared to an ordinal regression model because it may not require estimating many cut points. However, we are not done yet. Some further adaptations to the data must be made. One is to consider the limited range of values of the dependent variable. Adapting to this aspect of the data means correcting the residuals while estimating the parameters of the model. As a last measure to stabilize the results, the importance of outliers in terms of residuals can be reduced. There are several ways to do this. One is to construct weights based on the residuals and perform a robust regression. The rates directly counteract the leverage effect of the individual observations. Another way is to calculate the residuals relating to the conditional median, and that is to perform a median regression, of course. To demonstrate this with an example, we will use the Albus 2023 data. Once again, we do not use the whole data set, but the subset of the eastern states of Germany. The dependent variable y is the age of the youngest member of the household, DH17. As independent predictor variable, the age of the respondents is used. The distribution plot of the dependent variable DH17 shows us a strong skewness of the distribution. So, as a first step, we transform the dependent variable to its mean ranks. And as we can see, while the distribution of the dependent variable transformed to mean relative ranks does not correspond to a normal distribution, the distribution is less kinky than before. In a certain sense, the distribution is now symmetrical and no longer has any outliers. Okay, then let's state the formal model. The RLS estimate of the effect of age on DH17 is positive. The older the respondent, the older the youngest member of the respective household. The median regression comes to the same result, in this case even to the same value of the regression coefficient. A last thing which applies to ordinal regression as well to regression of the cumulative density of metric variables is to foster inferential robustness. This can be achieved by bootstrapping the confidence intervals. With bootstrapping, we avoid making assumptions in terms of distribution. A confidence interval for a regression coefficient then looks like this, where z is the correction term, and the inverse CDF is the quantile of the bootstrap distribution of the estimate for which the confidence interval is to be estimated. Applying this robust inferential statistic to the examples, we obtain this interval for the first example. So the effect of math f on PLM is statistically significant. The same for the second example in RLS regression. The effect of age on DH17 is also significant, and this is consistent with data from the second example, but median regression.